I have been hearing about the low noise level for loop antennas for a long time and always wanted to try out one. Two problems faced by me were the limited space available at home and the lack of a 4:1 matching transformer needed for a delta loop antenna. After a long period of brainstorming, I decided to try out a 2-meter full-wave loop antenna, as that is the one which can easily fit in on my small first floor terrace. An online search brought me straight to the full-wave loop antenna length calculator. There is a lot more information on that page than just a calculator for the length of the antenna. It has been mentioned that even though a circular loop is ideal, squares, triangles, and other shapes can work well, provided you can make the area enclosed by the loop as big as you can. That sounded nice and gives option to experiment with multiple shapes. A full wave loop can be used on frequencies higher than the design frequency as well. So I can use a 2-meter loop for 70 centimeter when I am trying to work amateur radio on International Space Station, at least for the high elevation passes. Let us see. Calculated the loop antenna length for uplink frequency of International Space Station, 145.990 MHz. It came to 2.10 meter. Checked for the transmit frequency of our local Tirur VHF repeater. That came to 2.11 meter. As usual, the advice is to make the antenna a little longer and then trim to get the best SWR value. The next hurdle was the balun. The calculator page had a solution for that as well. Feed point impedance of the design frequency is about 100 ohms. Matching can be done with a piece of 75 ohms coaxial cable, 1/4 wavelength long, shortened to compensate for the velocity factor of the cable. The page also gave a length of 0.34 meter for a 75 ohm coaxial cable with a velocity factor of 0.66 for polyethylene dielectric. If the dielectric is foam with velocity factor 0.8, it becomes 0.41 meter. Wikipedia mentions 0.75 as velocity factor for RG6U with polyethylene foam dielectric. U in this case stands for universal or general utility. In that case, it will be 0.39 meter for the Tirur repeater uplink frequency of 144.85 MHz. I am starting with that frequency for the loop antenna, as it will be longer than that needed for space station, and I can trim it later. Moreover, testing is easier as Tirur repeater is always available while space station is not. Formula for calculating full wave in meters is 306 divided by frequency in megahertz. Quarter wave matching section length in meters is equal to 75 into cable's velocity factor divided by frequency in megahertz. Feeder with parallel conductor lines will be best when using antenna on multiple bands. That is another project which I have been toying about and shelving for quite some time, mainly because I do not have an external antenna tuner, which they say is a must for matching a ladder line. I had this RG213 cable, which is 15 meter long, surplus after removing another 15 meter from the total 30 meters cable for my HF antenna. It has pre-crimped PL259 connector at one end. The other end is simply a cut end on which I'll have to work. This video clip has a better view of the PL259 connector as well as the other cut end of the RG213 cable. Here I have used the kitchen knife to strip off the outer thick black sheath of the RG213 cable partially so that the shield is exposed. Now a piece of the outer sheath has been removed and you can very well see the braided sheath surrounding the dielectric in RG213 cable. If you look carefully, there is a thin polythene sheet covering for the shield of the coaxial cable. You can see that now, and I'll remove that as well. If you look carefully, there is a thin polythene sheet covering for the shield of the coaxial cable. You can see that now, and I'll remove that as well. Now the copper shield has been twisted so that it can be joined to other wires, and you can see the dielectric in full thickness and also the inner conductor there. Inner conductor on close inspection is not a single conductor. You can see 3 wires there. Actually they are not copper, they are copper clad aluminum as I see. Here I have separated the strands of the inner conductor to clearly see that it is not a single conductor but rather a combination of 7 wires. They are thick wires, and central portion is seen as white or shining like aluminum, and outside is reddish color of copper. So I am sure that it is copper clad aluminum and not copper. This is the quarter wavelength piece of RG6 cable, and you can see that other than the shield there is an aluminum foil over the dielectric and the central conductor also. You can see. Check the resistance of that foil to make sure that it is a conducting material and not just a polythene. And you can see that the resistance is only 3 ohms. I have used crocodile clips to check the resistance with a multimeter. I checked the resistance between the aluminum foil on one side and the shield on the other side of the piece of coaxial cable, and as I expected it is a little more. It's about 9 ohms compared to the 3 ohms. There is some variation, maybe because of some fluctuation either in the connection or something else in the multimeter. Now I have prepared both ends of the 75 ohms coax piece and removed that aluminum foil, bad the conductors as well. Next I measured out 2.5 square millimeter insulated copper wire for the length corresponding to 1 full wavelength of the operating frequency and has kept it like a loop. Insulation has been removed partially and wires have been separated, that is the strands have been separated so that they can be fixed on the 75 ohms coaxial cable, which acts as the matching. One end of the loop antenna has been fixed to the shield of the coaxial cable using the multiple strands on either side, and the fixture has been insulated using insulation tape so that it will be firm over there without much movement. Now the other end of the loop antenna wire has been attached to the inner conductor of the 75 ohms coaxial cable and the junction secured with insulation tape so as to prevent movement and have good contacts. As I have not soldered it, it's a prototype and I don't want to solder it because I may have to adjust the lines. In the same way, I have attached the other end of the matching cable to the RG213 cable that is shield to shield and inner conductor to inner conductor, and secured well with insulation tape, so that the antenna is now ready. Just out of curiosity, I checked the resistance between the outer and inner conductors of the PL259 connector, and I found it to be around 45-46 ohms. This could be partly due to the resistance of the 15-meter coaxial cable and partly due to some loose contacts in the connections. Actually, the loop antenna will act as a short for direct current, and only for the tune frequency it will act as a 100 ohms impedance antenna. This resistance is DC resistance somewhere in the system. What remains is mounting this antenna and starting to test SWR, tuning. All those are tough jobs. I'll do it on another day.